Okay, so in today's lecture, we are going to continue the topic of Fourier transformation. Now, before we begin, so there are going to be four topics that we'll be primarily looking at. The first one is some examples and the properties of Fourier transformation. The second is what happens when we take a time domain signal, a continuous time signal, and we sample it, meaning that we discretize the signal in terms of time domain. If you recall, this operation of taking a continuous time signal and converting it into a discrete time signal is the very first block of a digital communication transmitter. It is known as analog to digital converter. And that process can be mathematically appreciated, and the concept behind the process of sampling a continuous time signal so as to get a discrete time signal can be appreciated using the framework of Fourier transformation that we are currently studying. Subsequent to that, the third topic is the topic of Fourier series that we'll be looking at. Now, what we'll find is that these two topics, the sampling in time domain and this Fourier series, they are kind of dual to each other. If we get a firm grip on the sampling topic, then by just changing our viewpoint, then we will see that what we get as a concept is this concept of Fourier series. So again, item number 2 and item number 3 kind of fall out of the duality relation of the Fourier transformation. And then finally we will be talking about the filters. What are they, what roles do they play, how to define them mathematically, and how to understand their operation in a conceptual manner. And there again we'll be making use of our convolution operation. Okay, so but before we proceed, I thought that there are some nice visualization that are available on the internet that allow us to appreciate the entire topic of Fourier transformation in a very clear manner, especially the part that I have emphasized repeatedly, which is that the Fourier transformation is a means, is a way of transforming our viewpoint. The signal remains the same regardless of whether our viewpoint is looking at the signal from the time domain perspective or the frequency domain perspective. It is it's just that we are kind of changing our way of looking at the signal, and that aspect of transformation of our viewpoint of looking at the signal is very nicely captured in some diagrams that we'll be looking at. And so for that, let us see this particular diagram which I have taken from this website. You can take a look at this website on your own in further detail. There is also a nice video that is embedded here. But what I want to bring your attention to is that there is one signal which, as shown here, it is comprised of two sinusoidal signals. One is at a lower frequency, the other is at a higher frequency. And their amplitudes also are different. Now, depending on what their relative amplitudes are and what their relative frequencies are, when we take a summation of these two signals shown over here, in the time domain we get either this blue colored signal, or we may get one of these gray colored signals, depending on how we combine these two sinusoids. Now, suppose that we are having this blue colored signal in time domain. One way is to just say that, okay, in time domain it has some two spikes, and in between those two spikes there is a valley here. But then the other way is to transform our viewpoint and say that there are actually just two frequencies which are present in this signal. The very first frequency is at this location, of this particular impulse, and its strength is somewhat larger than a higher frequency signal, which is this signal, whose strength is a little bit lower. So in frequency domain, the signal looks like this two impulses. If we transform our viewpoint in time domain, it looks like this uh, blue pulses or blue mountains with a valley in between. Now the nice thing is that it doesn't matter whether we call this as the frequency domain or this as the frequency domain. In fact, we can say that in time domain, maybe the signal is like this. Suppose we are given a signal which has two impulses like what are shown over here in the time domain. And then if we transform our viewpoint in frequency domain, now we will have a signal which looks like this. So time and frequency labeling is completely arbitrary. We can have a signal which looks like this in time domain or like this in time domain. And then we transform the viewpoint, it looks in the transformed manner as how it is shown here. So this is a very nice illustration which clearly conveys the effect of transforming our viewpoint. Instead of looking at the signal from this direction, we are transforming our viewpoint and looking at it from this other direction. A similar visualization is also here on this particular website. Here they are showing three different frequencies which are present in this red colored time domain signal. And so when we do the Fourier transformation, we get three spikes as it is shown here. So this is the transform domain viewpoint of the Fourier transform, which is particularly illustrative and something that I think you will benefit a lot by keeping this in your mind. Okay, so now coming back to our main four topics, let us consider the Fourier transformation of a rectangular pulse. A rectangular pulse has this mathematical symbol. It is denoted by this capital pi letter, and it is parameterized by the length of the pulse, which is denoted as capital T. And the definition of this rectangular pulse is that when the time is less than half of capital T, either in the positive side or the negative side, as it is shown here, the rectangular pulse has a unit value, as it is shown here. And then outside of this time interval, the rectangular pulse is entirely zero. One way to synthesize this rectangular pulse, at least mathematically, is to think of it as a unit step function which starts from minus t over 2. So there is a unit step function. It is 0 from minus infinity in time to minus t over 2, and then it is always plus 1. And then there is another unit step function which starts from t divided by 2. So it is 0 from minus infinity to plus t over 2, and then it is 1 afterward. Now if I call the very first one as u1 of t, the second one as u2 of t, then you can see that if I do u1 of t minus u2 of t, I will get 2 times this rectangular pulse. So that is another way to define this rectangular pulse. We have seen the rectangular pulse earlier. If you recall, when we did the pulse shaping examples, remember that time we did rectangular pulse, triangular pulse, and then we also had square root raised cosine and raised cosine pulses. So rectangular pulse is something that we have seen earlier in our convolution examples. Now let us try to understand the Fourier transformation of this rectangular pulse. So actually it turns out that the Fourier transform of this signal is pretty simple to evaluate, because when we plug in that capital pi t divided by t function here in the formula for Fourier transformation, first of all, the limit minus infinity to infinity, they reduce down to minus t over 2 to plus t over 2, simply because the signal is 0 outside of this limit. And so essentially what we have is an integral of exponential function with argument of minus j 2 pi ft over these limits. But this integral, as you know from your calculus class, is easy to evaluate. It has this particular form. And actually this is nothing but sine x over x type of function. Except now the parameter of that sine x over x is capital T times f. How did we go from second line to third line? There we have made use of this definition. Sine x over x, or specifically sine of pi over x over x over pi over x. And so if you do a simple derivation, you will see that the third line follows from the second line. So this is called the SINC function, and it is actually pretty much like a sine function, which is this numerator part, but it is not a simple sine function because of this denominator which varies with x. In fact, it is a damped sinusoidal function, and this dampening is happening because of this divide by x operation. Now when x is equal to 0, you have this indeterminate form. You have 0 divided by 0 type of form, and there again from your earlier math course you would apply L'Hopital's rule, and you will say that if you take derivative of numerator and denominator in the limit that x is equal to 0, you will get 1. So SINC function is defined for all values of x, and it turns out that it has this particular form. It's almost like a sinusoid, except as x increases, or in this case t times f increases, the value of sine keeps on continuously reducing. You will notice that at integer values of t times f, the SINC function is exactly 0. You see this? Now when did we say that this is a good property to have? Again we go back to our pulse shaping example. If you are transmitting symbols at this integer valued symbol duration, then this SINC function would be a good pulse shape theoretically, because it would not cause any adjacent symbol interference because of this property that its level becomes identically 0 at all integer values of t times f. Now that I have to qualify by saying that what we are looking at here is frequency domain view of SINC function. X-axis is frequency domain. In the earlier example, we were looking at the intersymbol interference from a time domain perspective. So what I just now said applies when we use this type of SINC function, not in the frequency domain but in the time domain. Okay. Now we have been looking at several Fourier transform pairs. Remember, we started out with exponential function, then we considered a sinusoidal function, and so on. Now we have one more such pair which we can add to our repertoire. We can add this pair in the list of Fourier transform pairs that we have so far understood. In the time domain, if I have a signal which looks like a rectangular pulse, in the frequency domain I'm going to get this SINC function. Now see the parameters of time and frequency domain. This capital T is the main parameter. Small t is obviously the time domain variable. Small f is obviously the frequency domain variable. It is the capital T which determines the shape of the pulse. As I make capital T bigger in the time domain, the effect is that this pulse is going to get wider and wider, because the width of the pulse is capital T, which is what I am making bigger. But let us see what is happening in the frequency domain. In the frequency domain, the first the immediate 2 points at which the pulse becomes 0 is actually 1 over t. Why is that? Because this axis is t times f. And so when I convert this horizontal axis, instead of making it capital T times f, if I make it just frequency f, then the location of this 0 points obviously becomes a multiple of 1 over t. Here it was just integer values, 1, 2, 3, minus 1, minus 2, minus 3. But that was because I am looking at t times f. Once I start looking at the SINC function as a function of small f, these points at which the value of the pulse becomes 0, they become multiple of 1 over t, as it is shown here. And the second thing is the height of this SINC function. That height is SINC multiplied by t. If it was not multiplied by t, then we know that SINC function at 0 is actually 1 by L'Hopital's rule. But actually, the Fourier transform of our rectangular pulse is not only SINC function, but it is SINC multiplied by t. And so therefore, here the height is a multiple of capital T. So what will happen when I make capital T bigger and bigger? In time domain, as we said, the pulse is going to get stretched out. It is going to become wider and wider. But what is the effect on frequency domain? The SINC here is going to become narrower and narrower, as well as taller. Its height is going to become higher. So that is again kind of a duality property, that if you have some signal in time domain and if you make it wider, if you stretch it in the time domain, in the frequency domain the signal gets compressed because of this 1 over t effect. So that is another kind of it's almost sort of like a duality property of Fourier transformation, that if you try to compress the signal, if you squeeze the signal in one domain, in the other domain, it kind of widens up or bloats up, and vice versa. Now again, we can directly apply the duality property and say that in this time domain, if I have a SINC function which looks like this, in the frequency domain I am going to get a nice rectangular pulse. So now this is something which we should hold a moment and consider why this is important. So the reason why this relationship is important is because if I am interested in transmitting a signal which occupies a bandwidth of capital W in frequency domain, this signal in the frequency domain has a width of capital W hertz. And so if I am interested in transmitting a signal whose spectrum, whose frequency domain representation does not go beyond plus minus W divided by 2, then I am forced to make the signal look like a SINC function in a time domain, where the intervals of the zero crossing is a multiple of 1 over W. Why is this important? It's because anytime a commercial communication system is designed, the designer always has to work with a given frequency spectrum allocation. You may have read about the wireless spectrum allocation in the newspaper. It is many times the front page news of a newspaper. The reason is because spectrum is very costly, and there are the government controls the spectrum, and it sometimes does the bidding. It does auctioning of the spectrum, and the spectrum gets sold to the buyers at a very high price. So spectrum is a very costly commodity, and therefore, if you are given a spectrum of some W hertz in frequency domain, then you have to make sure that your signal does not go outside of that W hertz. Because if you step outside of that W hertz, maybe you will be stepping on the spectrum of some adjacent system, and that the provider, the manufacturer of that adjacent system will not like that you are making your spectrum spill over to their allocated bandwidth. So so this diagram here is highly crucial in understanding. First of all, it shows to us what the bandwidth is of a signal. Bandwidth is nothing but the width of this rectangular pulse in frequency domain. And sometimes the signal does not have this nice rectangular shape in frequency domain, but if we loosely approximate the signal in frequency domain as this rectangular pulse, then the bandwidth is nothing but the width of that rectangular pulse. The second thing that it tells us is that if our bandwidth becomes larger, then our SINC pulse will become smaller in the time domain. And that makes a lot of sense. If you are operating over a large bandwidth, capital W, then by the information theory, the channel capacity theorem that we have studied at the beginning of the semester, the data rate that we can use goes up. The data rate is nothing but bits per second, or if we generalize it, it is symbols per second. Now, when we say that as we increase W, the data rate goes up, let us say in symbols per second, it means that in 1 second we are able to transmit higher number of symbols. But that is exactly what this SINC function is telling us, because 1 over W goes down, which means that each SINC takes a smaller and smaller fraction of 1 second, and therefore I am able to transmit more number of SINC pulses corresponding to each of these dotted lines. I'll be able to put one symbol here, another symbol at this dotted line, because it doesn't interfere. Remember, this SINC function value becomes 0, and therefore I'll be able to transmit far more many symbols in every second at each of these dotted lines. So as I increase capital W, my symbol rate increases, and that is something that we can see from this Fourier transform pair that is shown over here. Okay, so we'll conclude this video here, and then we'll start again from next slide onward.